Assalamu alaikum students. So let's look at an example before moving on to our next topic. This example is related to vorticity that we derived in the previous lecture. So given is a certain two-dimensional flow, and that is the equation of its velocity. And as you can see, this velocity has two components. One is the x component and one is the y component. And to find is this flow irrotational? What does this mean? That will this flow not rotate or will it rotate? So to see will it rotate or not, we will use our rotation formulas that we derived in the previous lecture. That was rotation along the x-axis, rotation along the y-axis, and rotation along the z-axis. We derived some terms for these rotations, and as you can see that this velocity has one x component and one y component. So to see that will it rotate or not, what we will do, we will take the rotation along the z-axis and put these components of velocity in that term, and we will see that will it rotate or not. For this flow to be irrotational, all these rotation components along the x, y and z must be 0. So as you can see, this is a two-dimensional flow in the x and y direction. So rotation along the x cannot occur, rotation along the y cannot occur because it is a two-dimensional flow, and the plane in which this flow is occurring is the xy plane. This is the xy plane in which this flow is occurring. So for this flow to rotate, it will rotate along the axis that will be perpendicular to these two axes, and that is the z-axis. So these two components of rotation are already 0. So what we will use is the rotation term along the z-axis, and we will put the velocity vector that is given in terms of x and y, and we will find out that is this flow rotation or not. So let's look at our equation. This is the u velocity vector and this is the v velocity vector. As you can see from here, we have already underlined it, and the z velocity vector in this case is 0 for this velocity field. For this velocity field, we are only given the the u velocity vector, the v velocity vector, and the z velocity vector. As you can see from the equation, there is no such term that is representing the z velocity vector here. So what we will use is the rotation terms along the x-axis, the y-axis. As we discussed, these two rotation along the x and y will be 0 because the flow is two-dimensional in xy plane. So what we will do, we will see a rotation around the z-axis, and we will use this term that we derived in the previous lecture, and we will derive with the help of partial derivative along the x of the v velocity vector, and with the help of partial derivative of y of u velocity vector, we will derive the terms from this u velocity vector and v velocity vector. So taking the partial derivative with respect to x of the v velocity vector, what we will get will partial over partial x, and this is the v velocity vector, that is minus 2xy. So we can only derive this along the with respect to the x, because if we take the partial derivative of this with respect to y, it will turn out to be 0. So what we will get from this derivative will be minus 2y, and similarly we will take the partial over partial y of this x square minus y square. So if you take the partial over partial y of x square, it will come out to be 0, and from this what we will get will only be able to derive this term, that will be partial over partial y of x square will come out to be minus 2y. So these are our two terms. This is the partial v over partial x, and this is the partial u over partial y. So now we can put these terms here instead of partial v or partial x and partial u or partial y, and these terms are minus 2y, and here also it is minus 2y as we derived, and by putting it in this equation, what we get is 0. So this flow is irrotational because all the components of rotation, that is along the x, y and z, are equal to 0. So this flow will not rotate, and it will flow in a linear manner, but it will not flow in an angular manner. So, or in terms of rotation, it will simply not rotate. So as you can see, this flow is irrotation, and to read out the comments in this example, what we have is that this is a two-dimensional flow, as I discussed earlier, that it is to be noted that for a two-dimensional flow field where the flow is in the xy plane, this was the flow in the xy plane, as I already discussed initially. Omega x and omega y will be always 0, since the definition of two-dimensional flow, u and v are not function of z. That's what we also discussed in the previous lecture, and this is what we already said in the start of the lecture, and w is 0. So here the velocity components, that is the u velocity component and v velocity component, are not a function of z here, and as you can see, the z-axis of velocity is not given to us. This is a two-dimensional xy flow, and the rotation that can occur will be along an axis that is perpendicular to these two axes, that is the x and y axes, and the only axis that is perpendicular to x and y is the z-axis. So what we did, we also saw the rotation in the z-axis, and when we put the terms here, it came out to be 0. So we derived that the flow is irrotational. And as you can see, the streamlines for steady two-dimensional flow of this example are shown in this figure, and as you can see, the streamlines are moving away from each other, so it will not cause any rotation. It is moving in this direction. They are moving away from each other. If they were to move towards each other like this, then it would have caused a rotation, but since we plotted this streamline, and in this figure it can be seen that the streamlines are moving away from each other, so in this case they will not cause any rotation. So this was related to vorticity, and this was our first example of this chapter. So now moving on to our next topic. So this is our next topic, that is conservation of mass, and by taking the conservation of mass principle, what we are going to do is we are going to derive a continuity equation in a differential form for a very small control volume. We already derived a continuity equation when we took a considerable amount of large volume, and for that large control volume, with the help of Reynolds transport theorem, we derived a continuity equation. So let's look at that first, and from that we are going to take some key points and we are going to use that to derive our continuity equation in differential form. So conservation of mass requires that the mass of a system remains constant, that we already know that the mass of the system does not change when we apply this principle. And if we see that in terms of what we did in the Reynolds transport theorem, we took our extensive property, that was B is equal to our mass, and we said that for the conservation of mass principle, the total change in the mass of the system must be equal to 0. So this was the left hand side of our Reynolds transport theorem when we applied that on a conservation of mass principle, and what we got on the right hand side was the partial change with respect to time in the mass inside the control volume, and the mass that is flowing into and out of the control volume through these control surfaces. So this was in the form of integral, and the integral form of this continuity equation was used for a considerable amount of large volume, as we already used this equation to solve our problems, and in those problems our control volume was considerably large, and what we did, we took the inlet and outlet of that control volume, and we were not concerned what was happening particularly inside the control volume from particle to particle basis. So what we are going to do now is write a differential form of continuity equation, and that differential form of continuity equation will be for an infinitesimal control volume, that is very small control volume. A very small control volume, we will going to derive a differential form of continuity equation. So this is our control volume term in our Reynolds transport theorem that we derive for our mass conservation, and what we got is the partial over partial t, that is the partial change with respect to time inside the control volume of this mass. So if we apply this integral, and if we take a cube, and that cube have sides of delta y, delta z, delta x, so the volume of the cube will be delta x, delta y, and delta z. So if we apply this integral on this dv, what we will get is the partial over partial t and rho v. So what we are going to do is we are going to write the volume, and we are concerned now is the our concern now is the change in mass. So this partial over partial t term will be applied on this density. So partial change of this density with respect to time, and we will get our volume. So this is the differential form of the change of mass inside the control volume. So this is the first term of our Reynolds transport theorem that was related to the control volume, and we use that to derive a differential term for the change of the mass inside the control volume, and this is the differential change of mass with respect to time inside the control volume. So this is what we derived by using the Reynolds transport theorem, by using the control volume term of the Reynolds transport theorem. So what we are going to do, we are going to now write equations for the mass that is crossing the control surfaces. So the mass that is crossing the control surfaces, we are going to take a certain scenario, and let's move to the next slide to see what that scenario will be. So in the previous slide, we derived a differential term for the change in density inside the control volume by using this term of the Reynolds transport theorem. So we derived a term that was partial change in density with respect to partial change in time inside a particular control volume, and this was our control volume, this cube right here. Now we are going to derive the differential term that will be the mass rate of flow across the control surfaces, that is representing by this control surface. So what we are going to do, we are going to see the mass flow rate that is happening across this surface. We will write equations for that and across this surface. So what we are going to do is we are going to find the mass flow rate across a particular axis, that is the positive and negative axis. After doing that, we will also write the terms for the mass flow rate across the z-axis and across the y-axis. So to do that, let's take this figure, and in this figure our original mass flow rate per unit area is this. This is in terms of density and velocity u. So this mass flow rate per unit area is in the x direction. This is the x component of mass flow rate per unit area. Why per unit area? Because you remember that our mass flow rate is equal to density, area and velocity. So here we don't have the term for the area in this term. So here we can write that this is the mass flow rate per unit area, and that is equal to rho v. So here the v velocity, it is represented by this u, and u is the x component of our velocity. So that's why we are calling this the x component of mass flow rate per unit area. So how will this mass flow rate per unit area change when it moves from the center to the right face, and when it moves from the center to the left face? So now let's look at these other terms that represents the change in the mass flow rate per unit area. So this is the original mass flow rate per unit area plus the change in the mass flow rate per unit area across a particular distance. So this gives us the gradient. This gives us the gradient. As you remember from the velocity gradient, this is the gradient for the mass flow rate per unit area. Means the mass flow rate per unit area is changing in a particular direction. and this is the partial change in the mass flow rate per unit area, the x component of mass flow rate per unit area in this direction, that is in the x direction. And how will this change when it moves from the center to this face? It will cover a distance of half of this delta x divided by 2, because it's moving from the center to this face, so it will cover half the distance of this. So multiply by this distance, that is delta x divided by 2. So this is the change, and to represent the total change we will add the initial mass flow rate per unit area. And to convert this m dot a into m dot, what we are going to do is multiply it with the area. So we multiply it with the area of this face. This is the area of this face, this delta z and delta y. So by multiplying this mass flow rate per unit area with the area, that is delta y and delta z, we will get this term in terms of mass flow rates. So this is the change in the mass flow rate, or as you can say, the mass flow rate on the right face of this cube. So now let's write the terms for the mass flow rate on the left face of this cube, because we have a positive x-axis and a negative x-axis. This was the mass flow rate across a positive x-axis. So what will be the mass flow rate per unit area when this mass flow rate per unit area changes across the negative x-axis? So that will be the original mass flow rate per unit area minus the change in mass flow rate per unit area across a particular direction. So this is again the gradient, this is the gradient, and this gradient is now across the negative x, and this is the distance it will cover from the center to the left face. This is again the total edge length, and this edge length from the center to this face will be delta x divided by 2, multiply by the area to convert that term, this whole term, into m dot, as we discussed previously for the right face. So now we have our terms for the mass flow rate across the right face and across the left face. So now let's see, this is the term for the right face, and for the left face we have the term of the mass flow rate per unit area. So to see the net flow across the x-axis, this is the this will give us the net rate of mass outflow in the x direction by taking this term and subtracting this term. So it will give us the net rate of mass outflow in the x direction, and by doing simple subtraction we will get this term, and this term will be called the net rate of mass outflow in the x direction, both in the positive x, that is both in the positive x and in the negative x. So it is representing both the net rate of mass outflow in the x direction, both in the positive and in the negative x direction. So now let's find the terms that will give us the net rate of mass outflow in the y direction, and in the z direction, so that we can write a generalized term for the net rate of mass outflow in these across these three axes, that is the x, y and z axis, and that will be our continuity equation. So let's see. So this is what we derived in the previous slide, that was the net rate of mass outflow in the x direction, and this is what it was equal to. And now let's find out the net rate of mass outflow in the y direction. It will be derived by the same method, but we are not going to repeat that. If you want to, you can, because it's the same, it will be derived in the same manner that we saw in the x direction. So the net rate of mass outflow in the y direction will be given by this term, that is the partial change in the mass flow rate per unit area in a partial change in the y direction multiplied by the volume in which this change is occurring, and then it is this the net rate of mass outflow in the z direction, that is the partial change in the mass flow rate per unit area in the z direction in this volume. So now combining these terms to get a more generalized term, and that will be a net rate of mass flow rate in all the three axes, that is the x, y and z directions. So by adding these terms and taking the volume common, we can write this net rate of mass outflow in the form of this. So what does this represents? If we see again our Reynolds transport theorem for mass conservation, we derived a term for this, and that term was in the differential form written like this, that is equal to the partial change in density with respect to partial change in time inside this controlled volume. So this term right here, the net rate of mass outflow, now represents the differential form of this term inside the control across the control surfaces, and the in the Reynolds transport theorem, this term represents the mass outflow and inflow across the control surface, and now in the differential form it will be represented like this. So this is the mass outflow across the control surface. So now adding this term and this term right here, we get our differential form of continuity equation. So this is the differential form of continuity equation. This was the integral form of continuity equation. This right here can be applied to large control volumes, and this right here can be applied to infinitesimal small control volumes, and that's why it is represented in differential form. So writing this in a more generalized manner, we can write this equation, and here is our partial t term, and the partial over partial x, partial over partial y and partial over partial z can be written in terms of the del operator and dot product with the density by taking the density common and the velocity vector, that is the u, v, w. So we have already written equations in this form. I hope this will be clear. This is the differential form of the continuity equation in a more generalized manner. Now let's see what will this equation behave when we deal with unsteady conditions, or with steady conditions, or with compressible fluids, or and with incompressible fluids. So let's see that. So this was our differential form of continuity equation, and this was the more generalized representation of this continuity equation in the differential form. So what if our flow is steady flow and the fluid is compressible fluid? So in that case, if the flow is steady, what will happen? As you already know, this term will be equated to 0, and we will be left with this term now. So this is our differential form of continuity equation for steady and incompressible fluids. Now this is how it will look like if we take the del operative and write it in the partial over partial x, partial over partial y and partial over partial z terms, and then multiply the density and velocity with its particular vectors. So this is now our differential form of continuity equation for steady flow. But what will it look like if we take incompressible fluids? Incompressible fluids, as you remember, their density do not change. So for incompressible fluids, the fluid density is constant throughout the flow field. So the density term will be neglected in that case. These density terms will be neglected, and this is how our continuity equation will look like if we just apply that for incompressible fluids and also they are steady. So this will be a more generalized representation. Now the density term is neglected because density is not changing, density is constant, and here if we write the del operator and the v velocity vectors, this will be our continuity equation in differential form for incompressible and steady flowing fluid. So this will be for incompressible fluids, and this right here is for compressible fluids, and both are steady flows. This is also a steady flow because the partial over partial t term here is also equated to 0. So this was our continuity equation in differential form. So now let's look at this example that is related to our continuity equation, and in this problem we are given a particular velocity field and the velocity components are also given. The x velocity component is given, the y velocity component as given, and what we need to do is to find the z component of velocity. So determine the form of the z component, that is w, required to satisfy the continuity equation. So the steady flow field is steady, so we will use the steady flow field continuity equation, and here the certain incompressible steady flow field, so it is also incompressible, so our continuity equation will be like this: partial u or partial x plus partial v or partial y plus partial w or partial z. So we will use this information to find this term right here. From this term we will get our velocity component, that is the z component of this velocity. So this is our continuity equation that we are going to use, that we derived for steady and incompressible flow. So right now what we need to do is to rearrange this equation in terms of partial w or partial z, and then find these two terms and write it in that equation. So partial w or partial z will be equal to minus partial u or partial x minus partial v or partial y. So this is what we are going to find, and then integrate this to find our w, the z component of our velocity. So this is what we are going to get by taking the partial or partial x derivative of the x component of our velocity. This is the x component of your velocity, and by taking the partial derivative of this u with respect to x, we are going to derive only this term, and these two terms will be equated to 0. So by taking the partial or partial x of this u, we are going to get 2x. And similarly for this term right here, we are also going to find the partial or partial y for this v velocity vector. So by partial v or partial y, we will only be able to derive these two components, that will be the xy and the yz. So it will come out to be x plus y, x plus z, as you can see right here. So writing these two terms in this equation, so what we will get is this. So our partial w over partial z will now look like this. This is minus 2x, that was the 2x that we derived here, and this is the x plus z that we derived for taking the partial v over partial y. So now doing a little bit math, we get this term right here. So now our partial w or partial z is equal to minus 3x minus z. So by taking this partial z to the right hand side, we will have partial w is equal to minus 3x partial z minus z partial z. Now integrating these terms, what we will get is the w, as you can see from this equation, we will get our w as minus 3xz minus z square by 2 plus c. As you remember, when we integrate a function without a limits, at the end of that integral we add a constant, because this is not a complete solution right now. We need to know the constant, and we also need to add that. So in this case, our z component of velocity is not particularly known. We cannot explicitly represent this z component of velocity with this term, because here still a constant that is a function of x and y will remain, and we still need to know this constant and add it with these terms to explicitly know our z component of our velocity. So this is what the comment section is also saying, that for the third velocity component cannot be explicitly determined since the function, that is the f of xy, can have any form and conservation of mass will still be satisfied. So the specific form of this function will be governed by the flow field described by these velocity components. That is, some additional information is needed to completely determine the z component of this velocity and to satisfy this continuity equation. So we still need to find that, but it is related to this particular example, we are not going to find this component. This is our final answer, but taking the solutions like this and having a constant at the end of our integral, we cannot explicitly define our z component of our velocity, and some additional information will be required to satisfy our continuity equation. So now let's look at this problem. We have three components of velocity in a flow field. That is the x component of velocity, that is given as x square plus y square plus z square. That is the y component of velocity, and that is the z component of velocity. In part A, we are required to see that is this flow linearly deforming, and is there a linear motion or not. So that is the volumetric dilation rate that we have to find. And in the second part, we are going to find that is this flow irrotational or not. So what we are going to do first is to use the volumetric dilation rate formula. So this was our volumetric dilation rate formula, and in this scenario we are going to take the partial derivative of this term with respect to x. So only this term will be derived, these two terms will be equated to 0. So taking the partial over partial u of this term will give us 2x, and then taking the partial v over partial y of this term, so what we will get is x plus z. That is this term will be derived, so the y will be removed, and in this case this term will be derived and the y will be removed, so we will be left with x plus z. And then this term, that is the z velocity vector, will be derived by taking the partial derivative of this velocity vector with respect to the z axis. So we will get minus 3x minus z. So we are going to add these terms, so we will put here the 2x that we had and the x plus z and plus minus 3x minus z. So now this 2x and x will come out to be 3x, and this z and minus z will cancel out, and we will have minus 3x and plus z minus z, and that is equal to 0 because all these terms will cancel out. So there is no volumetric dilation. There is no volumetric dilation. As you can see, the volumetric dilation rate came out to be 0. So now what we are going to see is that is there any rotation vector for this flow field, or is this flow rotational or not. So for that purpose we are going to use our rotational terms, that is the rotation along the x-axis, rotation along the y-axis, rotation along the z-axis. And similarly that we did, we will take the partial derivative of the x, y and z velocity vectors with respect to x, y and z. So I will just write the equations. The partial derivative that we will get from this, that will be equal to y divided by 2 plus z, and this will come out to be 5z divided by 2, and this will come out to be minus y divided by 2. So now adding all these, and we will get minus y divided by 2 plus z, that is the I unit vector, plus 5z divided by 2j and minus y divided by 2. Okay. So here the rotation vector is not 0, as you can see. So the flow is rotational in this case. This flow is rotational. So for part A, this flow was not linearly moving and deforming, but when we took the partial derivatives and saw the rotation vector with respect to x, y, z, so it came out to be a term like this in terms of ijk unit vector, and from this equation we can deduce that our flow is rotational and it will rotate, but it will not linearly deform, nor it will linearly move, but this flow is a rotational flow. So this was our first problem that was related to volumetric dilation rate and the rotation vector. So now moving on to the next one. Now in this problem again we have a velocity field given, and what we need to find is the flow, that is it irrotational and does it satisfy the conservation of mass principle. So the velocity flow is given in terms of the x and y components of velocity. This is the u velocity vector, this is the y velocity vector, and using these two vectors we are going to find that is this flow irrotational or not, and does it satisfies the conservation of mass principle. So let's find out. As you can see, the flow is two-dimensional because only the x and y component, that is the x component of velocity and that is the y component of velocity. So to find that is this flow rotational or not, we are going to find the omega z term, because this is a two-dimensional flow. One velocity vector is along the x, the other is along the y. So to find the rotation in this plane, we are going to take a perpendicular z-axis and find the rotation along this z-axis. So let's do that first, and then we are going to apply the conservation of mass principle and see that does it satisfy that or not. So first we are going to just use the rotation along the z-axis term, because there will be no rotation along the x and y axis, because as I discussed, this is a two-dimensional flow in xy plane. So the only axis that is perpendicular to the xy plane is the z-axis, and we are going to see only the rotation around the z-axis. So taking the partial v over partial x of this term, that is partial v over partial x, will give us 2y, because 2y, and taking the partial u over partial y of this term right here, what we will get is again 2y. So now put these terms in this equation right here. So omega z will come out to be half 2y minus 2y, and that will come out to be 0. So the flow does not rotate. This flow is not rotational, and the flow is irrotational, as it is already mentioned in the statement. So yes, this flow is irrotational because the omega z term came out to be 0. Now does it satisfy the conservation of mass principle? So before moving on to that, what we are going to derive from the statement is the flow is incompressible, and what we are going to assume is that it is also steady. So for steady incompressible flow, we will use our mass conservation differential form of continuity equation that we derive for the conservation of mass principle. So this is how it's going to look like. This is our differential form of continuity equation for incompressible and steady flowing fluids, and in this term too we are going to simplify it further, because we do not have the velocity vector z, we do not have this velocity vector. So what we will do is we will neglect this term and it will be equated to 0, because it is a two-dimensional flow situation. So we will only take the partial derivative with respect to x of the u velocity and partial derivative with respect to y of the v velocity vector. So taking these, what we will have is partial u over partial x will be equal to -1 minus 2x, and partial v over partial y will come out to be 2x plus 1. Now put these two terms here and here, what we will get is -1 minus 2x plus 2x plus 1 is equal to, and it will come out to be 0, because -1 plus 1 and -2x and plus 2x. So overall it will come out to be 0. So it does satisfy the conservation of mass principle. So yes, this flow satisfied the conservation of mass principle, because as you can see the continuity equation, the right hand side and the left hand side of the continuity equation are equal to 0. So yes, this flow field that is given to us does satisfy the continuity equation, and it is also irrotational. So that was our problem, that was related to see that whether the flow is irrotational and does it satisfy the conservation of mass principle or not. So hope that was clear.